Hi. First of all, nice to meet you all. I'm Dr. Belissa. I'm a first-year PhD student at the LPG, so the Laboratory of Planetology and Geosciences in Nantes, and I'm under the supervision of Tanguy Bertrand and Sabrina, whom just talked. And I'm focusing on basically what Sabrina told you just before. So can we use the alien processes as geomorphological markers to get better constraints of environmental condition in several celestial bodies? And I'm here to present the work that I have done during this first year on the Belissa deposit, where we ask ourselves the question, can the sublimation wave theory explain the blade of Tetarus dorsa? So to add a little more context, but Olivier White and Jeff Moore already did that this morning. The Belissa deposits are located in the Tartarus dorsal region, so a little bit to the east of Sputnik Planitia. They are composed of methane with a spacing of 2 kilometers up to 7 kilometers in some cases, and also a relief of about a mean relief of 400 meters, but it can go up to 7 and even 1 kilometers. And it developed on tens of millions of years old glacier. And also the low albedo that is unique in this area suggests that we are now, at least for present Pluto, in an active sublimation case. And in the last decades, there has been several hypotheses to try to explain the shape and the origin of the Belissa deposit. So there have been 4 hypotheses. For Moore and Tal, it's not 2017, but 2018. The first one is the endogenic extrusion, which is an analogy somewhat to diapir, and the second one is the one of Aeolian dunes, sorry. And then we have the condition atmospheric volatile with the high temperature at high altitude that allow only CH4 methane to condense, where N2 is not possible. And finally, we have also the penitentes hypothesis that have been said by Oliver White here, and also by Morse in his paper when he tried to model that. So if the first 2 were dismissed in the same paper, as this kind of process tend to occur rather in depression than in high elevation area where the Belissa are located. The second one, as Oliver White and Jeff Moore said this morning, is the area is on what it seems to be a sublimation state, or so we tend to think that it's more likely that the Belissa deposits are, at least for now, driven by a sublimation process. And finally, the penitentes hypothesis, I'm going to show you later on that the shape of the blade is not really similar to what we can measure with penitentes. And so we had several questions in the beginning of the PhD. So the first one is that there is no clear analogs of Belissa does not show clear analogs in the solar system, but is this really the case? And if not, can we link them to sublimation wave and to better observed in the solar system, and especially sublimation wave? And if so, as Sabrina presented you, can we use the new sublimation wave theory to get a better constraint on the environmental condition of the Belissa deposits? And also, can this theory explain the scale, the huge scale of the Belissa deposit? So in order to answer this question, we did a mapping of the Belissa deposit. It was already done, but in order to conduct the measurement, we did it again. And we measured the wavelengths and the orientation. And logically, it was the same result as the literature, with an orientation north-south of around 25-30 degrees mean, and wavelengths of 2 kilometers for the majority and up to 7,000 meters or 8,000 meters. And then what we've done is we did some cross-section in the Belissa deposit, so perpendicular to the crest, in order to analyze the morphology of the Belissa deposit. And what we saw here is that, so we have an example of a profile with the same scale in X and Y. And we took measurement of the aspect ratio, which is the ratio between the height and the length of a Brighterian deposit. And also we assessed the symmetry or asymmetry of the Brighterian deposit. And what we saw is that the Brighterian exhibit an asymmetry. The east-facing slopes are steeper than the west-facing one. We did it on almost 200 Brighterian deposits, and in 90% of the case it was that, and also an aspect ratio of 10%. And it's interesting because Bintaja, in his paper in 2001, that studied the blue ice area that Sabrina showed, he get the same result, so an aspect ratio of 10%, and also an asymmetry, and that we can see here. And it's funny to look that if we are scaling if we make abstraction of the scale, we have almost the same shape between the sublimation wave of Bintaja and the Brighterian deposit. And the same work was done on Mars with Bordiek, and it was also the same value, so 10% of aspect ratio and an asymmetry. So based on morphology, the Brighterian are looking similar with sublimation wave, but as Sabrina told you, the sublimation wave tend to migrate upwind, and we can see here. So if we look at the morphologies that we have, it tends to show that the wind above the Brighterian deposit is going from the west to the east. But as it was already said before, the simulation, especially from Tanguy in 2020, tend to show the opposite when for present Pluto, for 3 years of present Pluto, we have a wind that is mostly negative, and in this case negative is meaning from east to west. So it's kind of an issue with the morphological analysis and the physical conclusion, modelization. But as I will show you later on, we can think of several aspects to try to explain this disparity. And for example, to go back to the penitentes tend to show an aspect ratio of 2. They are really blade very high and not so length, and they are really symmetric. So we show that based on the morphology, the sublimation wave and the Brighterian deposit are similar. But we didn't know before the PhD if sublimation wave could occur on Pluto. So that's why we use the code and the sublimation wave theory, the stability analysis that Sabrina presented just before. And to do so, we use these values from the literature for the kinematic viscosity and the kinematic viscosity of the nitrogen and diffusion coefficient for the methane. As Sabrina told you, the Undine code is parameterized with the Schmidt number. And what we saw is that for very low Schmidt number, sublimation wave could occur only if the Schmidt number is superior to this value, so 0.01. And if we took all the Schmidt number values that can occur in Pluto year, depending on the ranges that you have here, we see that we are always above this value. So at least for the theoretical part, it seems that sublimation waves are stable in full Pluto year, at least for actual Pluto. And so what we saw also is that it's the same graph as Sabrina showed you, with a Schmidt of 0.0375. And we see that we have the gray area that represents the sublimation wave domain of stability, and also the dotted line represents the condensation wave stability. And so basically here we have one measurement for the sublimation wave and one measurement for the condensation wave. And next, we are applying the sublimation wave theory and the scaling law to see if, for example, the wind velocity derived from this theory is somewhat correlated or aligned well with the GCM estimation or the wind velocity estimation. So what we have here is the scaling law that we plot. So we have the Cassi plus that is an output for the code and the lambda that we measured. We have this dot line is for the Earth, so value for Earth, And we found this point correspond to the sublimation wave in Antarctica. This one is the one that has been done in Nantes, so in a lab experiment. And finally, this one is the one in the ice cave that Sabrina presented you just before. And we see that we measured the wavelengths and also the velocity, and it aligned really well with the line that is deduced from the scaling law. And if we do more or less the same work on Mars, what we have is that on the MNPC, we have some sublimation wave that you can see here with the wavelengths that is measured here. So it's more or less 5 to 10 meters, a mean of 7 meters. And if we run the model with the Mars condition and we just report this point up here, we have this point, and it's a wind velocity of between around 10 meters per second, which is well aligned with the GCM estimation around the Martian North Polar Cap. And finally, what is interesting for us is the case of Pluto. So in gray, we have the sublimation wave domain with the ranges, and in blue, we have the condensation wave. In pink, it's the wavelength that we measured on the Planetarian deposit, and the same histogram as before. And what you can see is that if we compare sublimation and condensation wave give wind velocities that are orders of magnitude higher than the one of sublimation wave. And if we look at, so it's wind at 10 meters above the surface, and if we look at the GCM outputs for the winds above the Planetarian deposits that we have here, and we take all the values that are represented here, we have this black line, and what we see is that it's fall right where with the estimation from sublimation wave. So we have an accord with sublimation wave theory and also the GCM estimation. So that's pretty nice. And so to conclude, what we saw here is that the morphology of Planetarian deposit is similar to sublimation wave with the same aspect ratio, the same asymmetry. The sublimation wave are theoretically stable on Pluto. We have a low albedo that suggests sublimation, which is cool for having sublimation wave. And we have the scaling law. If we apply it, we have the same estimated winds for the sublimation wave and the GCM. I didn't show it, but we ran the scaling law for the gross timescale, and it gives a timescale that is realistic for tens or hundreds and maybe million years of formation. And the scales that we observe of wavelengths is well explained with this theory. And the wind direction, as I said, was opposed, but we are thinking about several hypotheses to try to explain this. So maybe we need to explore past climate with the GCM that is currently being developed. We have also some regional effects because it's just a stability model. It doesn't take into account the katabatic wind, for example, and we know that on Pluto they have a really huge impact. And maybe mixed process with a mix of the paint and test process and the sublimation waves. That's something that need to be worked on. And finally, on the perspective, we want, as Sabrina told you, to do some more lab experiment to add more points to verify the scaling law. We want to investigate the condensation of methane at high altitude and to see how it can impact the growth and the erosion of the Planetarian deposit. And finally, use the GCM combined to the sublimation wave theory to try to model the formation of Planetarian deposit.
Question?
Greetings.
Hi.
Thank you very much. I think this is a very interesting, in a good way. Like, I think this is an important step towards trying to understand what's going on. So I have a couple of comments. So the sublimation wave theory is a linear stability analysis, and it's constructed from a base state that is net sublimating, and then you excavate out. The condensation wave theory is the flip of that, and as you showed, that there are now scales associated with the growth rate, the preferred growth rate of those patterns. So it's interesting that what you're suggesting is that on the scales that we're seeing the bladed terrain, the bladed structures, 2 kilometer, whatever they may be, they are in net, on average, undergoing sublimation. But the condensation wave preferred wavelength on that, it's about a factor of 10 larger, if 10 to 15 to 20 larger. When you look at this, the bladed terrain, you do see 200 kilometer scale undulating structure across the bladed terrain structure itself. So it makes me wonder if, in fact, on small scales you're seeing sublimation, but on the largest scale you're seeing a deposition wave structure appearing. And makes me wonder further, I wonder if this is a thing that is over the million-year time scale, it is drifting across in the longitudinal direction across the plane. So that, I think that was like kind of cool that there is that factor of 10 scaling you see between. So in other words, on that 200 kilometer scale, things are net in a depositional state. And obviously you're excavating on one scale and you're redepositing on the other scale. So that may be kind of an interesting kind of possibility. The other question is a comment, we can talk about this after, is how much temperature control is there in the sublimation rate, like say in the troughs of the bladed themselves? Because that may be a new extension of this theory to examine now how that controls, maybe how it saturates the depths of the bladed terrain themselves. That's right, or sharpens the tips. So I think this is all very promising. Thank you very much.
So for the first comment, it's something that we try to look at, but the condensation wavelengths that we were supposed to give we didn't measure them. It was not conclusive. But as you said, the bladed terrain may be on all the belts, so it's something that we can't really focus. But on Earth, for example, in Antarctica, we have this case of huge condensation wave, and on top of this condensation wave, we have smaller scales, sublimation wave. So it's something possible. And the second comment about the temperature, in the Ondine code, it's not really taken into account.
Right. So that's kind of an extension.
Yeah, and that's why we want to use maybe the GCM to try to do the first order work of the if it's stable, how much time it's going to take, and then use the GCM to try to model the formation with much more temperature-driven process and etc.